Borger High School chemistry students, this is Unit 4, Atomic Structure and History, and this is the third of the PowerPoints. So get ready. We're at the bottom of page 1 on your notes, and we're looking at number 4, the proton. The proton, now, the reason they started looking for the proton is that they realized that the stuff they were looking at was neutral. It had no charge. They had already discovered electrons, and they were negative. So if things were neutral, and you had all these negative parts, that means somewhere there had to be positive parts. So they started looking for these. You know, in order to be neutral, in order to be zero charge, you have to have negatives and positives, and they have to balance each other out. So that's what they started doing here. So this is what's at the very bottom of your notes. Now go over to page 2. And we have Wilhelm Wien in 1898 is credited with discovering the proton. So Wilhelm Wien, he discovered the proton. Alright, what do we know about protons? Other than the fact that Wilhelm Wien discovered them, we also know that B, they're positively charged. Proton, positive, remember that. Right. They are found in the nucleus. How do we know they're found in the nucleus? We can thank Mr. Rutherford for finding them in the nucleus. We'll get to him later. They're much more massive than the electron. We actually use the mass of the proton. When we start talking about the atomic mass number, we actually use the mass of the proton that's in there. And all protons look alike. Just like all the electrons look alike, all protons look alike. And what that means is, if you get a whole bunch of protons from different atoms and lined them up in a row, you wouldn't be able to tell which proton was from which atom. Right. Pre-AP people, you'll have to know Rutherford's experiment and be able to explain what went on with it. And that'll get more, we'll do that closer to the end of the PowerPoint. Now, number 5, if you find the nucleus on number 5 on your notes, page 2, in 1911, Ernst Rutherford, I just told you about him, discovered the nucleus. He's the one who figured out that, oh, hey, those protons are packed inside the nucleus in the atom. And he actually worked with J.J. Thomson in his lab, and also another guy that you might have heard of, and that was Geiger. He's the guy that invented the Geiger counter. It's the one that checks to see how much radiation you've been exposed to, which was kind of handy for those guys because they were working with some radioactive materials. Now, the nucleus is a tiny central area where the protons and the neutrons are found. The neutrons, this is number 6 on your paper, if the atom only had the positive protons and the negative electrons, then they should be able to calculate the mass pretty easily. But every time they calculated it, it was like twice as heavy as what they calculated it to be. So they knew they had to be missing something there. They had to be missing something. It's kind of like if we look at you and we say, oh, you're supposed to weigh, I bet you weigh 135 pounds. And yet, when we put you on the scales, you weighed 200 pounds. Well, 135 is what you're supposed to weigh, and you weighed 200 pounds. We'd start making you empty your pockets and checking for all the lead or the gold that you had in your pockets. There would be something we were missing there. And that's what they figured out with the neutron. It had to be something else there because the atoms always showed up heavier than what they expected them to be. So, the neutrons are found in the nucleus, letter A, on your notes. They're about the same mass as the proton, pretty close. They don't have an electrical charge. So protons have a positive charge, electrons have a negative charge, neutrons squat. They have no charge whatsoever. Neutrons, neutral, NEU, yeah. Neutrons are neutral, they have no charge. All the neutrons look alike. So all the protons look like each other, all the electrons look like each other, all the neutrons look like each other. You can't really tell from which atom or which type of element they came from. James Chadwick is credited with discovering the neutrons in 1936. So we started late 1800s, early 1900s, and went all the way up into the 30s before they had the basic pieces of the atom. James Chadwick. He's not one of the big 4. Dalton, Thomson, Rutherford, Bohr. I have a song for you that'll help you remember. And then James Chadwick is also credited with discovering the neutron. Alright, so here we have Rutherford's model of the atom. And if you look at the atom, it's got a lot of space where the electrons are orbiting, and then that tiny, 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 tiny little nucleus in the center where you'll find the protons and the neutrons. And this is kind of interesting. Someone said, calculated it, that if the Houston Astrodome, the whole Astrodome, were the entire atom, then the nucleus would be the size of a marble that someone set on the 50-yard line, which is just, kind of difficult to fathom how much empty space is in the atom. All right, here is Rutherford's famous gold foil experiment. And again, you may have to go back and pause this so you can write the information down. What he did is he shot large alpha particles, that's positive radiation. It's like a helium nucleus. So he shot them through thin layers of gold, and gold was the most dense material that he could get. That he could get also really thin too. Most of the alpha particles, they passed straight through, no deflection, they just went straight on through. Some were just a little bit deflected, like they bounced off something, and then there were just a very, very few that were really heavily deflected. They almost bounced straight back. This proved a couple of things. One, the metal foil, instead of being very dense and thick like they expected, it's actually very porous because things went right through them without tearing the foil. It's like there was nothing there at all. Even though we think of gold as really dense, that gold foil on an atomic level was really, really porous. Now, it also proved that the alpha particles were large compared to the electrons. So the electrons couldn't have deflected them. They were too massive compared to the electrons. It wasn't the electrons that were doing the messing up. The angle of deflection proved that the positive charges that deflected them were not evenly distributed. So what they're saying is you had J.J. Thomson's plum pudding model where you had the positive charges were just kind of evenly throughout with little negative charges in there. They're saying, no, this says by how they were deflected, it says that the positive charges were located in a tiny little central area. So that means there had to be a large mass of positive charges in the atomic nucleus. Only 1 out of every 8,000 alpha particles was deflected more than 90 degrees. So that means very little of them, very few of them were deflected. This means that the nucleus had to be really, 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 really small in comparison to the actual volume of the atom. And that means that it's also very heavy because that's where all the positive charges are found, and they're the ones that are really the heaviest things. Here you have a picture, and again you see a setup. You had the alpha particle emitter, and it was basically a radioactive material that was shooting out pieces of itself. And those alpha particles went straight through. The vast majority of them went straight through. Now, you see that blue detecting screen? That was kind of like a fluorescent screen that would light up every time alpha particles hit it. And most of them just, as I said, went straight through. You see letter B over here on the right-hand side, and that's actually showing you like what it would look like on the atomic level. Most of those, the little red arrows, the alpha particles went straight on through. But you have a few that are slightly bent, slightly deflected, and then you had that one that's severely deflected. Okay, atom's positive charge is concentrated in the nucleus. The proton has the opposite positive charge of the electron. And the mass of the proton, they calculated this out, is 1,840 times the mass of the electron, which is just massive compared to the electron. All right, so here we have a lovely atom again. Inside the nucleus, you've got the neutrons and the protons, and orbiting around the nucleus, you have the electrons. All right, we also have a little chart here that talks about the masses of the pieces of the atom and also the charges. You notice the neutron has mass, but it's got no charge at all. The proton has both a mass and a charge, and the electron has such a tiny, tiny, tiny mass that they just ignore it. They set it to 0. You won't even count it, but it does have a negative charge. So here we have like a little square from the periodic table, and it's got 2 numbers on it. In this case, the number at the top is the mass number, and the number at the bottom is the atomic number. The mass number, or atomic mass number, is the number of protons plus neutrons, with a symbol in the middle. And then we have the atomic number, and it's just the number of the protons. So at the top, we had protons plus neutrons. So if we have 2 protons, how many neutrons are there?